Here we'll talk a little bit about an introduction to exponential functions. Let's first define what an exponential function is. An exponential function is a function with constant ratios of outputs when inputs are equally spaced. So whereas with linear, you had a linear function, for example, and I'll just use generic variables right now, x and y, when the inputs were equally spaced, that's what we're referring to here, and you had something like this, where the change in y over the change in x was constant. So between 10 and 15, well, that was for a 1 unit increase in x, 5 unit increase in y. So we could say 5 over 1 or just 5. And same thing for all the rest of these. So the actual rate of change in the outputs when inputs were equally spaced was constant. Let's take a look at an example. This is kind of an older example, kind of a classic, and it's kind of a spin-off. So a worker chooses to be paid 3 pennies one day but asks for the pay to be doubled every day. Is this quote-unquote smart? Well, let's kind of see what this would pan out to be. So the day and the pay. So on day 1, or we'll just call this the initial day, so day 0, because that's how we kind of talk about years, the 0th year. On the 0th day, he gets 3 pennies. But on the 1 day later, he gets 6 pennies, because that's equal to 3 times 2. On the second day, on day 2, 2 days later, excuse me, he gets double this, which is 12. So that's the same thing as 6 times 2. On day 3, he gets 12 times 2, which is 24. 4 days later, he gets 24 times 2, which is 48, and this kind of evolves in this pattern. So this is going to be 48 times 2, which is 96, and by day 5 days later, he's earning 96 cents for the entire day of work. Now, this might not seem like a lot at first, but as we continue doubling and doubling and doubling, we'll notice that it's actually a big deal. So for a second here, I'm going to erase all of the work just so we have the final answers. And now let's see whether the change in the outputs is constant. Well, at first, from 0 to 1, the output increases by 3, then it increases by 6, then it increases by 12, then it increases by 24, then it increases by 48. So the change in P is not constant. But if we look at the ratio of what I'll call P new to P old, that is a lower value on the chart compared to a value that's higher on the chart, like these two guys, 6 divided by 3 gives me 2. 12 divided by 6 gives me 2. 24 divided by 12 gives me 2. 48 divided by 24 gives me 2. And you can kind of see the pattern that the ratio is constant. And so this is an example of an exponential function. Let's look at another one. In this problem, let's suppose you earn 10% per year on an initial investment of $100. How much will you have in 2 years? Well, there are probably a couple of different ways you'd approach this. One might be to say, all right, well, in terms of year and balance, year 0 would be a $100 balance. And to get 1 year later, I'm willing to bet that a lot of people would probably say, well, I'll take 10% of 100, and then that gives me $10, and then I'll take the 10 and I'll add it back to the 100 to give me 110. Well, that's a lot of work. Since we started off with the full original 100%, in other words, we started off with the balance of $100, which represented 100% of our initial balance, right? Whatever you put in, that's 100% of whatever you put in. Well, now I use this box to kind of represent the whole. Now I grow the whole, in this case by 10% more. So what do I have in total? Well, it's a 10% growth rate, as we would call it. 10% growth rate because that's how much we're gaining, but what do we have? We have 110% of the previous year.